In the last video, we built the circuit with the help of some friends. So we connected the resistor, the inductor together, like we have shown in the picture here. So resistor and inductor connected on the breadboard. And then we have the function generator connected to the resistor and then to ground in our circuit. So that's represented by this red clip right here connecting to the resistor. Then the black clip is connected to the ground, which is on the lower leg of the inductor. And then we're measuring the voltage across the inductor, which is VL, and we're doing that using this thing called an oscilloscope probe, which is this gray part right here, which is connected at the node between the resistor and the inductor, and its ground connection is this black alligator clip. So we have that set up. Now we'll go over and set up our function generator, and the function generator is set up right now. So we have a 10 Hertz square wave. It has a 1 volt peak-to-peak amplitude, and the offset is 500 millivolts. That means that the actual voltage excursions of the square wave goes between 0 and 1 volt because it's offset by 500 millivolts, or half of a volt, and its amplitude is 1 volt. So the duty cycle is the percentage of time high versus low, and 50% means it's half and half. And indeed, we could see that on the instrument, the oscilloscope over here. So we look at the yellow trace. Now it's time to tune up the scope. And we're on 100 millivolts per division. And it looks like it's going off the top of the screen right there. So we might need to change the vertical. And now we could see the top and bottom of the waveform. So we're 500 millivolts per vertical division. We're going 2 divisions. And we could see the 1 volt peak to peak of the square wave. So we could verify that it's a 10 Hertz square wave because our time base, our horizontal, is 100 milliseconds. So the period of a 10 Hertz square wave is going to be 100 milliseconds. And sure enough, every 100 milliseconds, we're going through a period of the square wave. So on channel 2, we have the voltage across the inductor. So that was the oscilloscope probe connection, the gray thing right here. And it looks fairly small right now, and we might have to make some adjustments in order to see it. So the first question is what are we expecting to see on here? So are we expecting to see the exponential asymptote to a new final value like we saw at the RC, or is it going to be a decay? So at first we could see there's a step right here, or a square wave bouncing up and down. But we got to look closer to really see what's going on. We'll get into why that square is there in a minute. The time constant of the RL we built is so fast that we're probably not actually seeing the behavior that we're looking to see. So in order to see that, what we're going to do is we're going to change the horizontal scale to a much smaller time division. And you can see there, everything's still looking kind of square. If you look really closely, might not be visible in the video, as I'm making the time base smaller and smaller, something's appearing in the middle of the screen. And there it is. So you can see there's some kind of exponential decay shooting up off the top of the screen, then decaying back down. So there's a good chance my vertical is not set properly on channel 2. And let's see, that looks good right there. I'll hit the stop. That makes the screen a little bit brighter so you could see it. So we could see what's going on right here. Time's moving on. Square wave steps high on the input on the yellow. And simultaneously, the voltage across the inductor peaks, then it exponentially decays back down. It doesn't look like it goes exactly to 0, but it does get low. And I could change the horizontal scale a little bit to see what happens here. I got to hit run again. Probably not going to be able to get 2 cycles in and see anything, but you can see there's a little bit of a step there still. See how it's stepping up, then down, then up, then down. And that's a non-ideal behavior. We'll talk about that in a little while. So when we're trying to look at the RL time constant, we're really looking at this peak right here and then the exponential decay. That's the thing that we're trying to measure. And I'm going to save this waveform for analysis.